We're connecting functions with first and second derivatives. So here we go. Okay. Let's say f of x equals 4. Four is a horizontal line, right? We all understand that concept. Y equals 4 is a horizontal line, 4 above the origin. Okay? Then, what is the first derivative of that function? 0, which is a horizontal line right here. What is the second derivative of that function? 0, which is a horizontal line right here. We're all good with that, right? That's 3 lines all graphed out for you. All right. Glad you're good with that. Let's do another one. Let's say that f of x equals x plus 3. Looks like that. Okay? What would be the first derivative of that function? 1. What would the second derivative of that function be? Notice how they're in 3 different places now. Okay? First one, the first, second derivatives are on top of each other. These were in different places. Okay. All right. Let's take another one. This time I'm not going to give you the equation. I'm so mean. F of x will be in red. That's f of x. What in the heck will its first derivative look like? Oh, you guys are smart. 2x. Because the graph, the red graph is what f of x equals x squared minus 2. So the first derivative is like that. Okay. What would the second derivative be? Would be that. Okay. We're getting good at this. Okay. Let's try this. Except for it can't be like that. It has to be like this. Can't have points. It's non-differentiable there. So that's why I had to do that. Okay. Here's a function. Okay. From here to here, and from here to here, the first derivative, I'm not exactly sure what it's going to be, but I do know one thing. I do know that from there to there, it's going to be somewhere like this, and then it's going to go like this, and then it's going to go like this, and it's going to go like this, and then it's going to go like this again. Now, how did I know where it dipped below the x-axis and where it went back above the x-axis and where it dipped below the x-axis again? Taylor Boothie, this is kind of important to understand. How did I know why we were dipping, going up and down and up and down, where exactly those happened? Because I know exactly that had to happen there, there, and there. Why? First derivative is slope. My first derivative, since my function is increasing, my first derivative will be above the x-axis. As soon as I hit my maximum point, then I start decreasing. So then when I'm decreasing, my slope is negative. So I'm going to be below the x-axis. Okay, so where a maximum occurs, you're going to have an x-intercept with your first derivative. Okay, hugely important for today. So you understand that. Where your maximum or minimums are, that's where you're going to have your x-intercepts for your first derivative. Okay, so I know it's going to be somewhere above the x-axis, somewhere below because we're decreasing, somewhere above because we're increasing, somewhere below because we're decreasing. How far above and below really doesn't matter all that much. Now, the second derivative is going to be something. Oh, I should have done that first derivative in green. Oh, well. Let's make the second derivative some wild, zany color like this. So the second derivative is going to be like this. And then like this. Now, how did I know that? Well, the second derivative tells me what? Acceleration when we're doing with speed and that. But what's our magic word we just finished with? Concavity. We're concave down. We're concave down. Let me change my highlighter. And then I go and close it. Good one. Let me change my highlighter to a different color. So we're concave down all until there. And then we're concave up. And then we're concave down all the way there. So where we're concave down, it'll be negative, the second derivative. Where we're concave up, it'll be positive. Okay? All right, I just explained this section in a nutshell. Now we're going to look at the problems. Okay? So these first problems will be a little easier than what I just got done explaining. Okay, let me go to purple. Okay. So the blue is a function. The orange is the first derivative. Why do we know that point C, why does it cross the x-axis there? Because it's a maximum point. Okay? Because it's a maximum point. F of C has the highest point on the graph. What's approximate calculation-based justification that it has a maximum point at C? Oh, the first derivative crosses the axis from above to below at x equals C. That would actually be the correct calculus definition of that. Even though those other two answers are correct answers for what's going on there, the best calculus-based definition would be that. What's appropriate calculus-based definition on why h has a relative minimum at x of c? Why does that have a relative minimum there? Because we are crossing the x-axis, so, and it's right below it, okay? What's appropriate calculus-based definition why h is decreasing? Because the first derivative is negative, and so on, okay? What's the fact that h is increasing? Because the first derivative is positive, okay? So you'll have questions like that. What's appropriate calculus-based definition that we have an inflection point? So this is the second derivative. Well, an inflection point happens where the second derivative crosses the x-axis. Okay, when the second derivative crosses the second x-axis, we have an inflection point. Okay. Here's a regular function. Here's the second derivative. Why is this concave down? Because the second derivative is? Because the second derivative is negative. If the second derivative is negative, it has to be concave down. Okay. So, given that the first derivative is 0 at point C, what's the justification that G has a relative minimum at C? Well, if the second derivative is negative, no, that doesn't help us. Relative max would be because it's concave up. Because if it's concave up, it has to have a maximum there at that point, if we know the first derivative is equal to 0. Okay. Why do we have a point of inflection at C? Because crosses the x-axis, which makes it a point of inflection. If the second derivative crosses the x-axis, it's a point of inflection. Now here's where the fun ones begin. Which one is a function? Which one's the first derivative? Which one's the second derivative? If you knew the function right off the bat, this would be easy. But you don't know which one is which. Okay? So you pick one. You say, okay, let's make this the function. So its first derivative would have to be above the x-axis from here on up to there, below the x-axis from here to here, and above the x-axis from here to here, and below the x-axis after that, just like number 3 is. So if this is g of x, this would be the first derivative for being above and below. Now the second derivative is the first derivative of the derivative, right? So this is decreasing from here to here. So it needs to be below the x-axis for this. Is this one below the x-axis until there? 1, 2, 3.5 over. 1, 2, 3.5 over. Yep, it looks like it. Then it should be above the x-axis from there to there. Okay, because we have to do the derivative because that's where it's increasing. Above the x-axis from here to here and below the x-axis. Hey, that worked out. And I just guessed on that one. So this would be the second derivative. Okay, so then the second derivative, we can look at the original one. Whoops. We can look at the original one for concavity. Concave down to from there, from here to here. Concave up till about here. So below the x-axis from 3 on over, above the x-axis till 1, and then below the x-axis again, concavity. Okay? So it goes 1, 3, 2. 1, 3, 2, which is this one. Okay? Let's look at another one of those. Okay? Just pick out a number, 1, 2, or 3, Joey. 2. Okay, let's just imagine that 2 is g of x. Okay? It's increasing until there, and then it's decreasing, if that's g of x. So the first derivative has to be above the x-axis until here, and below the x-axis after that. Okay? Well, so far, it's above the x-axis until about there, and then below the x-axis. So this could be the first derivative of this. So is 1 the first derivative of g? Well, from here to here, it's decreasing, so it should be below the x-axis from there to there. Is it? The answer is no. So we're off, but we know that this leads to that one. So let's see if this is g of x. If this is g of x, it's decreasing, so it should be negative until there, positive until there. Is it negative until 2, positive until 1? This one? Yep. So this would be the first derivative of that. And we know this one led to this one, so this is a second derivative. So you pick one out, and then you start seeing, well, what would be the derivative? And then you just keep going from there. So in this one, it would be 1, 2, 3. This one. Okay? Andrew, pick out a number. 1. So let's try to make this g of x. So this is increasing until negative 4. Are any of the, and then decreasing after that. So it should be positive until negative 4, and then negative after that until negative 2, and then it starts increasing again. So are any of them positive, then negative, then positive after that? Nope. Nope. So this is definitely not g of x. Okay? So then let's start with 2. 2, if this is the original function, okay, if this is g of x, then it should be below the x-axis until negative 4, and then above the x-axis after that. Look at that. This is below the x-axis until 4, and then above the x-axis after that, just by going with slopes. So we know this is the derivative of this one. So this is the first derivative of that. Then we'll see if this is the second derivative. Well, we are decreasing, so we should be negative until negative 1, 2, 3, 4, 5. It's increasing until negative 3, and then it's decreasing after that. So we should be below the x-axis till negative 5-ish, above the x-axis until about negative 3-ish, and then below again. Yep, that's a derivative. That's the order we go in. Okay? These are not the easiest of problems. 2, 3, 1, 2, 3, 1. But that's how you do them. Okay? That's your lesson for today. Let me put this out there for you.